So what we're going to be doing for this little mini unit is we're going to be looking at more complicated rational graphs, and we're going to start off by looking at specific characteristics of those complicated graphs. So I'm going to say that these notes are about the characteristics that you can find from the equation. So that's what the topic of the video is. What the topic of the next several videos will be is doing this, finding characteristics for complex rational functions. So complex rational functions. So we looked at more simple ones like 1 over x and 1 over x squared, or we could say 1 over x plus 3 or something like that. Here we're going to look at something that involves a little bit more. So that's the equation that we're going to be looking at. We're going to be finding the asymptotes for it. We're going to be finding the intercepts for it. We're eventually going to be graphing it and finding the domain and range and all of that stuff that we've been able to find in the past. So one of the first things we often look at as far as characteristics go is we look for transformations. And in these types of graphs, you actually can't see them. They can't be seen. So these don't really make sense to talk about a parent graph. It doesn't make sense to say it's been moving to the left or right. It doesn't make sense necessarily to say it's been reflected. And so for the transformations, we're just not going to look for those. Another thing that we talked about with the more simple graphs is we did mention that we have excluded values. And when we looked for excluded values, those specifically told us what our vertical asymptote was. Now in these more complicated graphs, it's possible to have more than one vertical asymptote, but that's one thing that we'll look for. Another thing that we're going to look for is what is called a hole in the graph. We're going to be looking for holes, and in a second I'll describe what that is. So to be able to find those excluded values, we know that excluded values come from making the denominator equal 0. So excluded values happen when you get 0 on the bottom of a fraction, because that's not possible. And so what we're going to do is we're going to take our equation that's written up here, and we want to factor the denominator so we can see what those excluded values are. So to factor that denominator, looks like I'm going to be doing a diamond problem. I'm looking for what multiplies to 2 but adds to 3. And the two numbers that would multiply to 2 and add to 3 would be 2 and 1. So on the bottom I have x plus 2, x plus 1. And then for the numerator, I can go ahead and factor that as well. X squared minus 1 is difference of squares. And so that's going to give me two sets of parentheses, one with a plus, one with a minus. The square root of x squared is x. And the square root of 1 is 1. So now I have the exact same equation, I've just factored it. And what you might be noticing after we've concluded last unit is that we actually have these two factors that seem to cancel out. So we can simplify that equation and say that those factors are the same and they would cancel to make a 1. And this is actually where a hole comes from. So a hole in the graph is just a missing point. So a hole is a part, and what it would look like is maybe you've got a curve, and suddenly it just skips a point. It just stops, there's nothing there, there's a little gap. So that's what a hole is, and you can find that missing point on the graph. So here, I would say that the number that would make this parenthesis equals 0 is x equals negative 1. So the x-coordinate of the hole there is negative 1. This is an excluded value because this is a point on the graph that does not happen. It doesn't work. And the reason it doesn't work is because it would make the entire fraction be undefined. You'd get 0 on the bottom right there. So the x-coordinate of the hole is negative 1. It's possible for us to find the y-coordinate of the hole. And the way that we find the y-coordinate is we take the negative 1 and we plug it into everything else. I'm not going to use the factors that I just canceled out, because if I put a negative 1 right here, it's going to ruin the whole bottom. It's going to make a whole bottom equal 0. But I can put negative 1 into the things that are left. So on the top, we're going to have -1 minus 1. On the bottom, I've got -1 plus 2. So on the top, that makes -2. On the bottom, that's +1. And so our y-coordinate must be -2. So I can conclude that that missing point on the graph is at -1, -2. We've got a missing point right there. So I'm going to go ahead and I'm going to keep track of all the characteristics that we found. So there's the whole. A vertical asymptote is an imaginary line that's going to be approached in this case, but it's not going to be crossed. So imaginary line that is approached but not crossed. And for us, that's going to come from the other excluded value. And so this is similar to what we saw with the simple rational graphs, is that whatever was on the bottom of the fraction told us our vertical asymptote. And so the vertical asymptote for this graph happens to be x equals -2. So -2 and -1 are excluded values for x. They're x values that you can't use. And they tell you very specific characteristics about these rational functions. All right, now that we've found a vertical asymptote, it would be good to find a horizontal asymptote. And horizontal asymptotes tell you some very interesting things about the graph, or there's more interesting ways to find them. So we saw equations before when we were talking about the simple graphs, and they had some sort of number on the end, and that was how you found the horizontal asymptote. And in these graphs, it's completely different. It's a completely different process. So for horizontal asymptotes, we're going to go ahead and describe them first. So like a vertical asymptote, it is an imaginary line that is being approached and on these graphs you might actually cross it. But just like all the other asymptotes we've seen, the curve will get closer and closer and closer to the asymptote. So it still acts like a normal asymptote, but in this case they might actually get crossed. The line might go across the asymptote. So a horizontal asymptote, you are able to find it by looking at the degree of the numerator and the degree of the denominator. So we have three scenarios, and when I say the degree of the numerator and the degree of the denominator, if you guys recall, the degree is the highest exponent, which when we put these equations in order, we usually put the highest exponent first. So the degree of the top of this one is 2. The degree of the bottom of this one is also 2. So these would have equal degrees for the numerator and the denominator. So we have three scenarios. The degree of the numerator might be less than the degree of the denominator, and in that case, the horizontal asymptote is y equals 0. The degree of the numerator could be equal to the degree of the denominator, and in that case, the y, or the horizontal asymptote is y equals, and it's the coefficient of the numerator, so it's the leading coefficient. I'm going to put LC for leading coefficient of the numerator, divided by the leading coefficient of the denominator. And we'll talk more about that in a second. And then the third scenario is that the degree of the numerator is greater than the degree of the denominator. And that means that for horizontal asymptotes that there isn't any. All right, and what actually happens here is there is what we call a slant asymptote or an oblique asymptote. All right, so slant or oblique. So that asymptote would not be vertical, it wouldn't be horizontal, it would be slanted. It would be a diagonal asymptote. So in the equation that we're talking about, we have y equals x squared minus 1 over x squared plus 3x plus 2. And when we look at this, we're not going to look at any part of the equation except for those degrees and the coefficients that go with those. So the number that goes in front of an x squared that's all by itself would be a 1. The number that's in front of this is a 1. And so since the degree of the numerator and the degree of the denominator in this problem happen to equal each other, then I know that my horizontal asymptote is going to be y equals the leading coefficient of the numerator, in that case this is 1, divided by the leading coefficient of the denominator, which is also 1. And so our horizontal asymptote is the line y equals 1. All right, next we're going to go ahead and look to see how we might find our intercepts, so x-intercepts and y-intercepts. So to find our x-intercepts, we know that you always write them with a number for the x-coordinate, and then the y-coordinate is always 0. There's no exceptions to that, it's always 0. And to find the y-intercept, you know that you're going to have a number for the y-coordinate, and then the x value is always going to be 0, no exceptions. So for us, we want to ask the question, if we're finding the x-intercept, we want to know how to make y equals 0. If we can answer that question, then we're going to be able to find the x-intercepts. And if you look back at the original problem says y equals this fraction. So if I want to take this equation, y equals x squared minus 1 divided by x squared plus 3x plus 2, I want to know how to make y equal 0. So I need to take the equation and set it equal to 0. Now, it's not as hard to solve as you might think it is, because if you look at this, we have a fraction that we need to make equal 0. And the way that you make a whole fraction equal 0 is if you take the top of it and make the top equal 0. So 0 equals x squared minus 1. So I'm going to go ahead and take the top, I'm going to factor it. So 0 equals x plus 1 and x minus 1. And the reason I'm factoring it is because the factored form is how we solve a quadratic that looks like that. And so this x would equal negative 1, and this x would equal positive 1. Now the graph that we're talking about actually only has one x-intercept. And the reason for that is because if we look at our notes, we already found that the x value of negative 1 was a whole. It can't be an x-intercept if it's also a whole. So x equals negative 1 is not an x-intercept, that's a whole. And so x equals positive 1 is the x-intercept that we have. So there's our x-intercept. To find the y-intercept, we just have to make x equal 0. So if we consider our equation, we're going to have x squared minus 1 divided by x squared plus 3x plus 2. And what happens here if I do 0 squared, that's just 0. And 0 squared is also 0. And 3 times 0 would also be 0. And so when you're looking for your y-intercept, you can basically just look at the numbers on the end of the equation. And so here we're going to say that our y-intercept is 0 for the x-coordinate, and the y-coordinate would be negative 1/2. All right, now I'm going to take all the characteristics that I just found, and I'm going to combine them all into one graph so I can see how all these characteristics make it possible for us to sketch a pretty accurate graph without using a calculator. So if I look back at my notes, I know that I have a vertical asymptote at -2 and a hole at -1, -2. So here's our vertical asymptote. And then at the point -1, -2, we're going to have a hole in the graph. We have a horizontal asymptote at the line y equals 1. So I can go ahead and draw a horizontal line right there. I know that I have an X-intercept at 1, 0. So I can go ahead and draw that. And I have a y-intercept at 0, -1/2. So at this point, since we know how asymptotes work, we know that the curve is going to go through these points and then get closer and closer and closer to the asymptote. And if you go ahead and graph it on a calculator, there's the calculator, so we know that one curve goes over here and one curve goes over here, which kind of fits what we're used to. And to find some other points, you can go ahead and look at your table. These are -2 is an error, -1 is an error because that's where the hole is, -2 is an error because that's the vertical asymptote, and then I can see some more points there. So -3, 1, 2, 3, 4, and 3, 4, 5, -5, 2, and we can say that's probably enough for us to be able to sketch the rest of this because we know how asymptotes work. And then there's a sketch of this more complicated graph.